So hello guys, you are watching LearnACAD. In this video, we will see about how to determine the complexities. So we can determine the complexities based on the type of the statement used by the program. So let's begin with the video. The first is constant time, which is big O of n. We can say it big O of n. So in the following operation, take constant time. The first is assigning a value to some variable. And the second is inserting the element in an array. The third is determining if a binary number is even or odd. And the fourth program is retrieving the element I from an array. And the fifth one is retrieving a value from a hash table with a key. So these following operations take constant time because they are simple statements. In this case, we say the statement time is big O of n. So let's consider an example. Int example equals to 1. So in that example, we are assigning a value 1 in the variable example, which is a type of int. Now we will discuss about its graph. So as you can see in the graph, constant time is indifferent of input size. So declaring a variable, inserting an element into a stack, inserting an element into unsorted linked list, all these are statements take constant times. So the next one is linear time, which is big O of n. So the next loop executes n time. If we assume that the statement inside the loop is big O of 1, then the total time for the loop is n into big O of 1, which is equals to big O of n, and it is also known as linear time, as you can see in this example. And here are the more example of linear time, which are finding an element in an unsorted collection or an unbalanced tree. And the second one is sorting an array using bubble sort. And in this graph of linear time, we can see how the running time increases linearly in the relation to the number of the elements n. And the next one is quadratic time, which is big O of n square. So in this example, the first loop executes n times. For each time the outer loop executes, the inner loop executes n time. Therefore, the statement in the nested loop executes a total number of n into n times. So here the complexity is big O of n into n, which is equals to big O of n square. So this should be avoided as this complexity grows in quadratic time. Some more examples of quadratic time are performing linear search in matrix, and the time complexity of the quicksort, and the third one is time complexity of insertion sort. So this is the graph of quadratic time. So algorithms that scale in the quadratic time are better to be avoided because once the input size reach n equals to 1 lakh, we can say the time it will take is 10 seconds to complete. And for n equals to that value, time can be 16 minutes. And for n equals to that value, time can be 1.1 days. So you get the idea. So the next one is logarithmic time, which is big O of log n. Logarithmic time grows slower as n grows. An easy way to check if a loop is log n is to see if the counting variable, in this case the variable I, the counting variable doubles instead of incrementing by 1. So in the following example, int I doesn't increase by 1 because it is I equals to I into 2. It is not I plus plus. It doubles with each run. That's why traversing the loop in log n time. Some common examples of logarithmic time are binary search and insert or delete an element into a heap. So don't feel intimidated by logarithms. Just remember that logarithms are inverse operation of exponential something. And logarithms appear when things are constantly halved or doubled. And this is the most important line, which is logarithmic algorithms have excellent performance in the large data sets. So this is the graph of the logarithmic time. And the next one is linearithmic time, which is big O of n into log n. Linearithmic time are capable of good performance with very large data sets. As you can see in this example, the first loop is linear loop and the second one is logarithmic loop. So the total is linearithmic loop, which is big O of n into log n. And some more examples of linearithmic algorithms are heap sort, merge sort, and quick sort. And this is the graph of linearithmic sort. And here is the conclusion graph of all those four complexities. A comparison of the first four complexities might let you understand why for large datasets we should avoid quadratic time and strive towards the logarithmic and linearithmic time, as you can see in this graph. So thank you for watching this video, guys. If you have any query regarding this video, then you can type your query in the comment box or you can ask on the Instagram. The link of the Instagram is given in the description box.